dehydrogenation between CO2 over methane containing small pore zeolites.
Number 2.
That's this one. So hi, welcome everyone. My name is Michiel Dusselier from Belgium, from KU. I'm a research professor in a group doing zeolite synthesis, catalytic conversions, and also some integrated plastic synthesis. So today I would like to talk about combining these two passions, let's say, CO2 conversion as well as small pore zeolites. But before we go into that, we have to talk a little bit about DHP, the dehydrogenation of propane. Both with and without CO2, and our focus will be later on combining CCU, so converting CO2 to CO as well as propane dehydrogenation to propylene. To know whether this makes sense to look at the CCU aspect of CO2-assisted dehydrogenation of propane, we did a limited LCA to look at the benefits or mineral benefits for this conversion, as well as the CO2-assisted the non-CO2-assisted DHP versus the classic production of propylene and other products. Finally, after this LCA, we're going to go into catalysis, where we did a very broad screening on aluminum of all the active elements that we thought were interesting. And the second or last part of the talk, we will deal with taking one of these elements, or a few of them, and putting them on in and on small pore zeolites to see whether these materials can also catalyze ODHP efficiently or not. So the reason we want to study propylene synthesis, of course, is the propylene gap. So propylene is made from FCC, fluid catalytic cracking. Or second source of propylene is steam cracking, where there's like the green bar is also quite a heavy source of propylene. And then in China, mainly there's C2O, coal to olefins, there's some MTO. But in the recent years, there's a gap between the demand and the production. So that's kind of one of the issues. Propylene, of course, is used to make polypropylene, acrylonitrile, propylene oxide, etc. And the second aspect, besides the gap, which is kind of the demand for on-purpose propylene production, there is the greenhouse gas emissions of propylene production, currently estimated at about 2.8 kilograms of CO2 per kilogram of propylene as a function of the unit, which are quite high values. But this is a weighted average of all the production technologies combined for this synthesis of propylene. The FD, which is the fossil fuel depletion impact, is also quite high, but not as extreme as the greenhouse gas emissions for making propylene. So, to counter, let's say, the propylene gap, people have developed the PDH, which is quite a commercial success in recent years. So there are a lot of varieties of processes. None of them, of course, with CO2. This is the pure PDH with propylene converting to propane converting to propylene and hydrogen, an endothermic reaction, and there's a lot of varieties. So you, for instance, have the cut-off process running on chromium oxide on aluminum. There's the famous PDH by BASF doing something with platinum and tin. Also, Overflex is a well-known process on alumina with platinum and tin promotion. These materials usually are run between 550 and 650, and they're doing relatively low pressures. Some of them use a bit high pressure, like Overflex, that go up to 3 or 4 bar. The conversion of propane is about 40%, but this is actually because it's an equilibrium reaction, and the space velocities are decent. So, to go into the details of PDH, we have to look a bit at the thermodynamics. So PDH on its own has this profile, which we calculated in Aspen at 1 bar. Gives us a profile like this, so you indeed have this conversion level of about 40 to 50% at 600 C. If you're going to add CO2, there's two ways that you can model this or you can interact. First one is you do an indirect mechanism. So you take a hydrogen that's produced in the PDH, and this hydrogen is then doing a reverse water gas shift reaction to make CO and water in an endothermic reaction, so the REGS. And combined, you have the production of CO and the production of propane. If you do this, you get a bit higher. Conversion of propane, because you're pulling the equilibrium away because you're converting the hydrogen. On the other hand, you get a little bit conversion of CO2 as well, but it's not as high as the propane because the REGS equilibrium doesn't allow for that. If you model it in another way, which is the direct way, you get the red one. You get a bit lower propane conversion, so your propane conversion is below the PDH level, but the CO2 conversion is higher than the propane. So these two are actually on top of each other in the red curve. If you would be able to do it directly, which is not a given or which is maybe economically not feasible, you would convert as much CO2 as propane, and from a CCU perspective, this could be an interesting idea. Of course, thermodynamics is one thing, but on the other hand, you need to look at some material that can do it kinetically. And then, of course, you could have the blue route, which we discussed as an indirect pathway, where you have your DHP, can happen on a radioxide catalyst like chromium, can happen on a metal catalyst like platinum. And this is kind of a rate determining step, the DHP step. And on the other hand, to produce hydrogen, you would do REGS on different sites or other catalysts that you have added. Versus the red mechanism, the direct mechanism of CO2-assisted PDH would be you co-convert them at the same time. And so the active first step is the dehydrogenation of propane. We get the production of water immediately, and then this catalytic surface is regenerated by the oxidation of CO2 directly. So it's not a REGS, but it's the reoxidation of the surface by CO2 itself. In literature, this is supposed to be the slow step. If you look at pure DHP, the dehydrogenation of propane, so it would be the abstraction of the first or the second hydrogen. In the oxidative version, the direct mechanism, there is not really an agreement. It could be that the reoxidation with CO2 is slower, but in some cases also people have seen that the first PDH is also slow, so it's not clear yet. But then we ask ourselves, is it worth the trouble to investigate the CCU perspective of CO2-assisted PDH? We did this limited life cycle analysis. So life cycle analysis took into account classic PDH on one hand, simulating the entire Aspen plant, or a limited version of the Aspen plant, versus the indirect mechanism where we had CO2 and propane in equimolar mixtures from the start at 1 bar, and then having this whole product scheme of hydrogen, CO2, propylene, and water. And the next version, of course, we simulated is the direct mechanism, where we assume that no hydrogen is formed, only CO, CO2, water, propane, and propylene remain. So here the separation train is a bit simpler because we don't really separate the hydrogen. But these are ideal scenarios, so here we take into account thermodynamic conversions and sensitivities were reached, so not no-side reactions. Looking at this limited LCA, we define two impact parameters, the greenhouse gas emissions per functional unit of propylene, and the other one is the fossil fuel depletion, so the top and the bottom. So we simulated this at different pressures and different temperatures. The general trend in all these plots is that if you go to higher temperatures, you start to drop in GHG emissions, but of course our simulations cannot be taken into account above 700 or 650 C because the side reactions will be much more dominant than the main model's reaction. However, at lower temperatures, if you go too low, then your space-time yield and your equilibrium for this endothermic reaction will be low, which also will give you very low productive setup. So ideally, you would look at 600 C and compare the values at different pressures. Pressure in general is bad because you're making more molecules than you're putting in. So thermodynamically, you would not prefer to work at pressure. Although in the process even it would have some benefits to use high pressure, for instance, in some of the distillations or the pressure swing absorption setups. Anyway, our model is quite good. given that the DHP impact from literature, from GHG, is indeed about what it is on Earth for 1 to 3 bar. So this is the start. This is the North American impact from publications for PDH without CO2. If you compare it to the Chinese impact, where they use coal to make coal to heat their plants rather than shale gas to heat their plants, the impact of the process is much higher. So this line here that I did mention is the line of the current propylene greenhouse gas emission impact. So everything can be compared with this line for greenhouse gas emissions for fossil fuel depletion. And then the current levels of DHP can be compared to indirect ODHP and direct ODHP. So if we compare these three, we see that there's a significant, there could be a significant benefit for greenhouse gas emission reduction if you would do direct ODHP. So you would have a 1 kilogram of CO2 emitted per kilogram of propylene produced versus maybe 1.5 for the DHP versus, of course, a huge number for the classic production with the polluting C2O, SC, FCC mix. So these three scenarios already point that there could be some benefit to CO2 assisted ODHP. Where does it come from? It comes from here. So in this plot, we have the greenhouse gas emission savings or distribution among the different parts of the setup. So the propane feedstock is going to be the same. The CO2 is the main driver for this reduction in greenhouse gas emissions because of converting CO2 as a greenhouse gas. Heat and electricity is quite similar for these three ways of operating, and the plants also look quite similar. The total cost so is about 50% lower for the DHP when assisted in the direct way with CO2. So there seems to be a lot of greenhouse gas benefits or potential greenhouse gas benefits if you would co-convert your CO2 ideally in a 1-to-1 ratio with your propane. And you would even be able to make these numbers negative if you would, let's say, sell the CO that you produce in these mechanisms or the hydrogen that you produce and replace production by SMR, by the steam reforming of methane, which is a very polluting technology to make CO and to make hydrogen. So if you say that these products can also be counted towards the LCA, you would even gain up to 3.4 negative emission of 3.4 kilogram per kilogram of propylene produced. So these are huge theoretical values, but they indicate that there is a potential to study this reaction. So if you would calculate, for instance, that all the current DHP plants are revamped to include CO2 and they go to an indirect mechanism, you would have some savings of about 70 to 90 megaton of CO2 equivalents per year, which could be quite impactful. But of course, to get there, you need some catalyst that is able to really do these kind of mechanisms. So, and we don't even know they're out there. And if you look into the literature, there has been a huge body of literature on PDH, a huge body of work on O2 assisted PDH, but not that much on CO2 assisted PDH. Although there's some works out there, mainly based on chromium, some named some gallium. But in many of these works, and you can read about it in these excellent reviews, for instance from Ian et al., they don't really mention a lot about the fate of CO2. So CO2 is converted to CO, ideally, but you don't, in many of these papers, you don't find the mass balance for CO, you don't find the conversion of CO2. So it's not really from a CO2 perspective that people have studied this. They have only looked at propylene production, and maybe we can alleviate coke by having CO2, or maybe we can regenerate the catalyst a bit because of CO2, or we can avoid propylene polymerizing because of CO2, but not really from a CCU perspective. So that was how, let's say, what we set out to do. Of course, where to start? We took many of these elements. In total, we did about 20 different active elements on aluminum. Aluminum is a good commercial support and also has a good heat transfer profile. We did acidic wetness for many of these elements and then calcium them at 600 before testing. Interesting colors can be obtained in many of these materials, especially because of looking at the redox type of materials, where we would have potential to find these much more different type mechanisms where the CO2 can indeed reoxidize the surface in the catalytic cycle. So that was the goal, finding direct mechanism of materials so we can produce as much CO as we're producing properly. This is our setup. It's a plug-full isothermal setup where we can also do temperature transfer control and measure all the C1 gases as well in 2 different columns and 2 different detectors to measure CO, CO2, methane, but also all the hydrocarbons quite accurately. And of course, when you do the CO2-resisted PDH, you have a lot of products that can form. For instance, you have of course, the DHP, the ODHP, the reverse water gas shift. But then on top, you have if you have CO2, you can do the reverse with water reaction. You can get scope to be transformed into CO, and you can also have cracking. But then you can also have a classic PDH. But another one you can't have in classic PDH is the DRP, the dry reforming of propane, where you can make propane into hydrogen and CO. So these are additional reactions that can occur, especially at high temperatures. This is our protocol that we followed for all these catalysts. So on the top slide you see a molar flow kind of perspective. So we have a 1-to-1 CO2 and propane, and then we have a temperature run program here. The temperature is around from 400 to 600. In some cases we go even higher. Then we regenerate, and then we do the same again, but at a higher pressure. So I wanted to look at CO2 resistant PDH, that's 1 bar more or less, and then 6 bar, to get a feel for the reaction order as well, although this is not a kinetic type experiment. After that, we do regeneration, and we do a time stream test at 600 stream, looking at the deactivation of these materials, and we do it again at 2 pressures. What you see here is the vanadium. Vanadium is an interesting material because, as you can see, the blue and the red symbols are on top of each other. So it's propane conversion as well as CO2 conversion are quite similar. So this would already point to the fact that it may be a direct mechanism catalyst that has capabilities of doing CO2 reoxidation on the sites with CO2 directly rather than doing a reverse water gas shift. Another thing to notice here is that the selectivities are decent at, let's say, 600, although we have some coverage, which is also taken into account in the mass balance. So opposed to some papers in literature where you only look at the hydrocarbon selectivity, where they look at propane and propylene, and they balance the two, saying, okay, propylene selectivity is this high. We have a mass balance which takes into account everything in molar flow. So also the propane is calculated based on the in situ time stream profile we have this selectivity as well. And so the colors here you see in many of the slides coming is the selectivity for the whole, for everything that happens to propane. So propane can do ODHP, so that will be propylene production. Gray is propane, the green, the yellow one is cracking, so this is making methane and making ethylene. And then the reforming is the DRP, the dry reforming of propane and CO. Where you can also see that we have some dry reforming of propane, if you look above this line, you can see the molar flow mass balances of CO2 and propane, and you see that, for instance, here we have some production of CO, the little blue bit, above the middle line, which means it's coming from the blue part, from the propane part. So this is DRP being produced, producing CO. So all this screening led us to extrapolate from the temperature where we have activation temperatures for both propane and CO2. And for the time on stream, we then follow the deactivation kinetics a little bit. So we have all these parameters plotted out in our paper, which is about to be hopefully published. So you can really compare all these different metals that have been sometimes reported but never reported with the full CO2 balance on their catalytic properties. If we rank them from low to high space temperature for propylene, that's what you get in the bottom graph. You have the highest or the most active elements are chromium. We tried a couple of different supports as well, but that's not important today. Gallium is quite okay, vanadium is an interesting one, and then there's a whole range of different catalysts. And for some of them, the CO production is higher than the production of propylene. For others, it's a reverse. So there's clearly a lot of different mechanisms happening at the same time. Some interesting materials, of course, chromium that was the top catalyst, or was also very close to the industrial one that's used in the catalytic process to do DHP without CO2. We see a good selectivity, especially at low temperatures, and this is the conversion of both propane and CO2, but the conversion of propane is much higher than the conversion of CO2. So this is clearly an indirect mechanism catalyst that is doing some RVGS with the produced hydrogen. In the time of stream test, it's quite stable. Selectivity is decent, but again, CO2 conversion is quite minimal. What we did in another test was assess pure RVGS for each of these catalysts that were interesting. And that's this graph. So in this graph, you see the selectivity of CO for the same catalyst and a different experiment. You see the extent of the equilibrium for RVGS, and then you see also what we obtain in terms of conversion of CO2 and hydrogen, which is here the feedstock of RVGS. So you see that it gets quite close to being a decent reversible gas shift catalyst as well at 600C, which is not surprising because it is an indirect mechanism CO2-assisted OPDH material. Other key catalysts for cobalt. Cobalt has not been tested a lot before in this reaction. Cobalt is also an indirect mechanism catalyst, so there is again a lower conversion of CO2 versus propane, but it is quite a stable time on stream, although at low activity for cobalt, so it's an interesting material, but it also depends on what temperature you calcine, because it can form cobalt 203 or cobalt O or different spinels, even with the support, so it's kind of a whole field that could be studied with this cobalt. In terms of reversible gas shift, it's not that close to equilibrium, but it can still do some RVGS. Cobalt was also a bit interesting because at higher temperatures we noted that it was quite good in the reverse good water reaction. So alleviating coke, so that's what you see here. There's almost no coke in these stream tests. Another interesting one is gallium. Gallium is a mix of gallium, indium, and tin, about 80% of gallium, and it behaves very different than gallium. Gallium is a very indirect mechanism catalyst. It's quite good at DHP, it's not good at converting CO2, but when we alloy gallium oxide with tin oxide and indium oxide, we get much more direct behavior with the conversion of CO2, and propane is very similar to each other. So that was an interesting material. And another interesting one is indium. Although indium is a special kind of material because it's very mobile at higher temperatures. So indium, as you can see, is less active in the lower temperature zones, but it is the only one where we get a higher conversion of CO2 than of propane. So it's converted a lot of CO2 in many different paths. As you can see, also the selectivity for PDH is not that good, so it's only about 60% of propylene form. All the rest is DRP, cracking, and some coking. But we discovered that this catalyst is quite good at RVGS. So if you look at the RVGS behavior, even already at these lower temperatures, it makes, it almost achieves the equilibrium conversion, so we could not detect any other product in the GC. So CO was the main and only product. And this was not reported before we did for indium or aluminum. We also saw some interesting restructuring during these RVGS trials, and we calculated the activation energies to be lower than the classic iron, etc. based catalysts. But that was a side point. So after we do all this screening, we have some interesting materials. We try to attribute each of them to direct or indirect behavior. For the direct one, as I told you, we have the direct production of CO and water, but no hydrogen. On the other hand, you have RVGS coupled to PDH. Indeed, you have for the two very distinct materials here are vanadium. So vanadium on aluminum here has for instance, in the early temperature zones, which is kind of the initial or the most representative catalytic behavior. You have low CO over, or you have CO over propane ratio that almost climb to 1 and then kind of plateau. And only at higher temperatures you start doing other reactions producing CO. But the propane, the hydrogen over propane ratio is very low in these zones. So this kind of points to the fact that you don't have a lot of hydrogen production or a direct type of mechanism. Chromium, on the other hand, you see that the blue dots are already above the line, so it's close to 1. So it's a very indirect type of mechanism. Indeed, at higher temperatures you get side reactions, etc. Or reactions into producing hydrogen, producing CO. And the extent of the reversible gas shift really matches the theoretical extent of the CO over propane ratio. So that's the black lines. So it's quite clear which catalysts are which. And with this overview, we can go back to other screen materials and make a table kind of pointing out which ones are more direct, which ones are more indirect. And that's the whole idea of the review, kind of catalytic review by experience. Based on the conversion propane and CO2, the balances of hydrogen propane and CO2 propane. That's kind of what we did here. So interesting elements, or vanadium, molybdenum, magnesium. Although vanadium is the most active of these that we mentioned, indium is also a direct mechanism catalyst, and bismuth is also quite interesting, although not high in conversion, it could be a good one to alloy with different metal oxides. When we take the whole screening and we put them on a plot, we plotted them versus the Tamman temperature. So Tamman is half of the melting temperature of a material. We plotted them versus the Tamman temperature of the oxide, which we assume is kind of the acidic form present during our reactions. Also based on our information on calcination, no pre-reduction. We found an interesting correlation between the Tamman temperature for these pure gold oxides and the conversion of CO2 divided by the conversion of propane, which is kind of the primary parameter to point out direct versus the mechanism of CO2-assisted PDH. We clearly saw that there was a correlation. The correlation improved if you don't take these hollow symbols, and for these hollow symbols, it was quite clear that they reduced during the reaction. So for indium, we found in certain cases metallic indium formed. For silver, gold, platinum, these are not really materials that have the whole marsh palladium kind of stuff chemistry. So if you exclude them, the mobility parameter, so the Tamman temperature is kind of a mobility indicator, because it's kind of half of the melting temperature, when the oxygen already starts to move around, but the material hasn't molten entirely. It's a good indicator for finding a direct mechanism of catalyst. So that was our interesting find. Or you could also use some of these elements to tune maybe the Tamman temperature of alloys, which, like we tried with the galvanstone versus galvan case. Galvanstone is a metal which is almost liquid at room temperature, whereas gallium is this is the oxide, but the metal is also much more rigid than the galvanstone alloy. So it seems that the Tamman temperature is a nice indicator for perhaps finding more direct mechanisms of catalysts. We also tried to model all our reactivity data with oxygen vacancy formation from DFT with another group, but their correlation was much less clear than on Tamman, which is just a parameter from the numbers, which is quite interesting. So intermediate conclusions, LCA is pointing to real benefits. We did a wide experimental screening. Vanadium is cool, cobalt, bismuth, molybdenum, manganese, indium can be interesting, maybe also to co-alloy with vanadium or other elements. The Tamman as a guide can be also a guide for your support, because of your oxidative interacting with your support. There might also be more mobility and oxygen vacancy formation tendencies, who knows. So the focus was on DO-GHP. We found vanadium was a really interesting element, but of course if you say mobility and Tamman, you also think about maybe we should confine these materials in pores or on supports where they're not moving around too much. You want them to be reactive with the CO2 and with the species, but you don't want to segregate or aggregate large clusters. So that's why we go to the next step. We try to make confined vanadium, etc., small pore zeolite results. This is another graph, I don't plan to discuss it, but it's one of these vanadium catalysts in more industrial, like UDHP conditions, and they still perform more or less the same as in our screening. Vanadium, this is the one we choose. And in the literature, there's a couple of interesting mechanisms proposed for a small vanadium cluster consisting of a V5 and a V3. This is a group from Marin, Galvita, and Ghent. They have proposed a V5 V3 that then is able to do the hydrogen extraction to a V4, another hydrogen extraction on the same vanadium. So this vanadium is V3, and then expels propane, it expels water, and it's reoxidizing in this step with the CO2 coming in a hydrolytic exposure of CO2. So that was the ODH kind of cycle for this cluster of E5 and E3, but it could also do PDH on the same type of experiment. They DFT also did over the DFT to prove a DH kind of cycle. The rate extent that each case was the same, so it was the first hydrogen abstraction. But the difference in the hydrogen abstraction is that the second one is actually done on the bridged vanadium or vanadium. So whereas in the case of the direct CO2 assisted ODHP, it's on the same vanadium. So this one gets two hydrogens from it, and then it becomes water. Of course, this is all just a theory and hypothesis. So we wanted to see whether we could confine some of these vanadium clusters on small pore zeolites or other zeolites, because there has been a lot of literature on the chemistry of vanadium and molecular vanadiums, and even Carrero pointed out that there was maybe a chance that small vanadium crystallites were formed right before the monomer that were especially active in PDH with some convincing evidence. So this is kind of the situation we're looking at. Also in literature, we tried to look in PDH to see whether people had really done small pore zeolites for vanadium or other zeolites, but we didn't find a whole lot. We found a lot of cyclical supports and aluminum, but without CO2 even. We found some report on silicious beta, but again with no CO2, and beta is already a large pore material, so small pore zeolites are missing. If we look beyond vanadium, we thought maybe we should look for chromium or zinc or all these other elements. Maybe there have been some small pore zeolites tested, but we found none, or very few. There has been some reports on Safa 34 with the plasma and tin catalysts, but not really with zeolitic forms. We found an interesting, on the right side is more like micropores materials. We found some interesting silicate one situations with zinc and copper in recent ACS analysis, for instance. But again, no small pore zeolites. The closest thing we found is with CO2 is a beta related chromium, but again, chromium is not a direct mechanism catalyst, it's more of an indirect behavior. But they saw some interesting behaviors when supported on beta in the presence of CO2. But again, no small pore zeolites. So why small pore zeolites? They are really nice materials. I spend a lot of time trying to synthesize them, and now we try to use many of them. So there's a review where you can read all about them. So they're good for NTO, they're good for DNOx, SCR. Some people use them for metal synthesis in the past, and maybe again in the future. So we tried a couple of small pore zeolites. But first we wanted to see whether our element was the right choice of vanadium, which has vanadium, indium, and molybdenum on a CHA 40, so it's a whole-weight silica aluminum 40, mole per mole chabazite zeolite. And we saw interesting effects that at first, so the space-time yield of propylene was increasing already. We did not expect it because we go to a confined material, maybe there's some transfer limitations or something. Secondly, selectivity is the gap between CO production and propylene production is narrowing, so it points again to maybe a more direct type of mechanism than on the dull aluminum. So this is on dull aluminum. And the third thing is selectivity is also increased a bit, and mainly because the gray bar is lower, which is the coking selectivity. So a small pore zeolite, as expected, kind of prevent coking or hard coke to form. This is our hypothesis. So next we tested a couple of small pore zeolites with different gauges, because if you hope that vanadium goes inside, maybe the confining can help you steer to a different, maybe mono or D atomic cluster of vanadium. Not really with good success, so vanadium on CHA is still the best in our case. The only one that's a bit interesting is DDR. So we will explore that in the future, although the space-time yields of CO and propylene were still much lower than the aluminum. So in fact, this one where the two are on top of each other with CHA 40, as in many of these papers here today, and also with our Stacy zones, but often we test very exotic zeolites, but chabazite then turns out to be the best for some reason. So some synthesis structure activity relations, it doesn't work with every chabazite. So we tested, for instance, pure silica chabazite, but as you know, you cannot make a pure silica chabazite with small crystals easily, and we were also not able to do it with small crystals. So this one, being on silica chabazite, this huge crystal, so it's 5 micron, and we expect that the vanadium has no chance to go inside really easily in this procedure. So there may be other procedures to get it inside, but we did not really see it. We did a vanadium on CHA 15, so there's much more aluminum in the framework, versus the 40 versus the 7. So here you have two effects playing. The first one could be more acid side, meaning more cracking, more DRP, more side connection, more coating as well. But on the other hand, if you have aluminum, this could be a pull to pull in the vanadium during the preparation, because it's a kind of an ionic pull for the positive cations that should come in. So vanadium on CHA 40 and 70, the best one is the CHA 70, so you don't need a lot of aluminum, but we could never test the hypothesis that you don't need any aluminum if your crystals were small enough, because we could never make any vanadium on silica CHA or a silica CHA with very small crystals, meaning 0.1 micron or something. But we're trying to work on that. When we did the big crystal test of CHA 15, we get the same result again as the pure silica. So no activity, and we don't even want to plot the selectivities because the mass flows of the product were too low. On the other right side, you see a CHA 70 with half the loading of vanadium. So we just decreased that by a factor of 2, and it's still quite visible, which kind of points to the fact that it's not just a simple more vanadium, more activity, but it's probably a specific cluster that is formed that is doing all this reaction. However, when you draw that, you see that the activity is decreasing a little bit, probably because not all your aluminums are then covered by vanadium or involved in something with vanadium, which means that they probably do some cracking or some cooling. Interesting also that all the results were at 6 bar, so for all the zeolites that we tested, for most of the zeolites, the high pressure experiments were more successful than the low pressure experiments, pointing to the fact that maybe there is an effect of the order for propane and CO2 in these pore materials where the confinement is of course much more heavy than on the aluminum. So this, for instance, is a 6 bar profile, this is a 1 bar profile. We did some characterization so far, but we're not done yet with our full study of the vanadium speciation in these small pore zeolites. We did some XPS, so here conveniently we did some oxygen binding energies, and this is the vanadium signal. So the vanadium trifluoride, which was an intermediately good catalyst, here we see the vanadium, so the more they shift to the left, the more interaction with support you expect, the more higher binding energies of the vanadium. On the other side, the oxygen can point to vanadium O vanadium versus vanadium O silica. In this case, this shoulder points out vanadium O vanadium. So this catalyst was not ideally prepped, it seems. Also, the vanadium O silica from the XPS, which is kind of the first nanometer of the surface, or the first nanometers, was a bit higher than what we would expect. So in this material, vanadium is still maybe 30% or something is still on the surface. But after reaction, we saw that it kind of moved to higher binding energies for vanadium, and also the shoulder disappeared. And also the vanadium on silica on the surface decreased. So it's going inside, and it's finding a different place, and maybe it's stabilizing itself in that way. And also, it's probably not anymore V2O5 on the outer surface, because the binding energy of the vanadium seems to have shifted to the region of V5 or V4, heavily interacting with silica. But this is still preliminary. The best catalyst, the vanadium Dusselier, had none of these issues anymore from the fresh preparation from the start. So this material was already without V2O5 signals and with high interaction with the silica in the vanadium XPS. Also, our 10DX showed us no big vanadium clusters or not even small vanadium clusters, and a very good dispersion of vanadium all throughout the crystals. But mind that these crystals are quite small, so they're like 200 to 500 nanometer for this specific sample, which you need to do custom synthesis for you achieve, let's say, good support for vanadium-based CO2 assisted ODPH. Finally, we looked at cyclability, because as you know, in the cut-off process with the chromium support, they're using maybe 3 years, they're using this catalyst, and it's recycled like 40,000 times or something. So if you want to design a catalyst that does work like this, you also have to have good cyclability and regeneration capabilities. So we have a 54 catalysts. The orange one is called aluminum. Then we have the SHA-15, which was okay, but had a lot of cracking side reactions. The 40 and the 70, which was the best one. And indeed, for all of them, after each cycle, 2-hour cycle regeneration of the air, they all come back to the initial high activity. And the plot that you see for selectivity is the one for the best one, so the SHA-70. Keeps producing a lot of propane and CO, and has very few side reactions, or limited to, let's say, 10 to 15%. Then we did some fitting of this deactivation profiles, and we found two regimes. The initial hour, we see a very sharp decrease of our, let's say, highest activity, and then a very stable decrease. And when we split this into like the first hour deactivation fit or the full range of the experiment deactivation fit, we get two KDs, deactivation rate constants, which are very different, and when we fit the global deactivation constants with the silica to aluminum ratio of the zeolite, it kind of fits nicely with the idea that too much aluminum is doing cracking side reactions, whereas if you don't have that, you don't have any issue with deactivation, or less of an issue with deactivation. So that was kind of interesting. Again, going to the fact that if you extrapolate this line to pure silica, you will get a really nice material if you give the extrapolate to most vanadium without having an ionic pool from aluminum. That's the hypothesis. We're not going to go into here, but a little speculation to end maybe. So this is the model that was proposed by the Galvita group again. So V5PO3. But of course we have aluminum, maybe there. Some proton around, so who knows that we have some different kind of mechanism where the hydrogen abstraction from the propane, or the second one or the first one, maybe it's going to the bridge one, maybe going somewhere else, maybe it is. much faster, or maybe the CO2 reactivation from 3 to 5 is different, who knows. That's what we're trying to figure out in the near future. But for sure, a 2 vanadium atom cluster could be hosted inside the cage, although this is really a stupid figure. It gives you an idea that maybe we can do within this kind of 1 nanometer confined cages. And all the evidence of our reaction points to that. And it also points to the fact that CO2 and propane can be eliminated here. So there's a host of things we can now try with these small pore zeolites. We did some kinetic modeling, but maybe it's too much to go into detail, but indeed we see that they are behaving also direct mechanism, not indirect, and the order of reaction is different than on aluminum, which was again seen in the high pressure experiments as well, where there is an order effect in our kinetic modeling. But anyway, and then we found another zeolite catalyst, which I cannot discuss, but it's about 70% higher than the small pore zeolites that I presented today. But there's a lot of exploration space for everyone to try, I would say. So when LCA was performed, DHP and indirect even ODHP has a lot of potential. A lot of potential for CO2 emission reductions. We should search for direct mechanism catalysts, guided maybe by atomic temperature, as we've shown. Small pore zeolites, medium pore zeolites could be exceptional, and the small confinement could help you make a cluster which is really active, who knows. So research can begin. I'd like to thank my group in Belgium, so mainly Michael, a very good postdoc, but also Mira, Jose, and Ram, and Thibault, and the people I collaborate with for XPS and GAT and in Louvain for TFT. And all of you for your attention. Thank you.
So we have time for one question. Anyone has a question?
Great talk. In one of the slides, I can see the molecular ratio between hydrogen, propylene, and CO of 1 to 1 to 1, I think. Where you've shown the ratio, the average ratio. Have you considered at some point, for example, for the vanadium, where you have 1-1-1, to do the hydroformylation reactions, because then you would allow to convert all your stream into one product, and while you would limit the downstream process.
It would be a good idea. We haven't considered that. We already have not considered that. It would be a good idea because the one delta CO2 or DPH is the lower version of propane, so we could push that by something else. It would be